Hello, everybody, and welcome to episode 32 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Mike, and that is Gavin. Gavin, it's no longer Shark Week. What animal deserves their own week next?
Well, like Shark Week started, pretty much any animal that we're killing indiscriminately. There are so many to choose from.
Should we have a week just for animals that aren't being killed by humans? Just because that'll be easier and more manageable?
See, but here's the thing. I don't know of any. Because my first thought was, okay, what animals are doing real well with humans, other than our domesticates, things like our pets. And there's really not many. Deer,
Jellyfish?
I guess that'd be a neat jellyfish week. That doesn't sound nearly as well as Shark Week would.
No, not even a little bit. It sounds incredibly boring, to be honest. But
but as some of my favorite podcast hosts, a podcast that I listen to quite a lot, and if you ever listen to it, you'll notice that this podcast takes quite a lot of inspiration from them, is the Common Descent podcast, another paleontology focused podcast. They've said multiple times that both of the hosts are under the firm stance that any animal, any species is interesting enough to have its own full-length documentary about it, and I completely agree. Just because, even things like earthworms, they're just incredibly interesting. Would that documentary get viewed? Probably not.
we'd watch it.
I'd watch it.
Absolutely.
I might have to have a couple adult beverages to, sort of go through it, but I'd watch it.
That's just the way it goes. Here's the thing, is that I'm not 100% sure I agree with that because I don't know the subject matter well enough. At this point, I'm convinced that any species can have an hour-long podcast dedicated to them, no problem at all.
Pretty much. There are some exceptions with, circling back to earthworms. We have basically zero fossil history of them because they have nothing. They have no hard parts. So they don't leave good fossils.
So then we can have people on for speculation about what had, how they evolved and all of that.
Yeah, for sure. Absolutely.
So you guys know the drill now. You can check the links in the description if you want to be a guest on our show, if you have a topic you'd like to cover, or if you would like to check out the show on Twitter where we post a whole bunch of cool things that are happening in science. You can check all that out, as well as anything that we talk about will be in the links down in the description. And speaking of cool things happening in science, this episode is going out on July 21st. So is there anything fun going on July 21st or at any other point in this week in history?
Yeah, there actually is some geologically relevant things going on. So this is a weekend, so it's a twofer. So do you have a date for me? Or a year?
2010.
Nope. Swing and a miss on both.
You'll
get another one eventually, I promise.
Yeah, I'm
statistically
yeah, I'm 1 for 20 something at this point. So.
Yeah. So the first one is from July 17th, 2008.
Okay, I wasn't that far off.
And
they've been getting much later as the calendar's been going on.
Well, the second one, which we'll talk about afterward, is from 2018. So it's So yeah, the first one from July 17th, 2008 is single boulder links Antarctica to North America. I have not yet read this one, but to my knowledge, I don't believe Antarctica has ever been directly connected to North America.
I have several questions.
Based on this calendar's track record, I highly doubt that they will be answered, but I'll do my best.
They might get answered, just not well.
just not well. So, experts from the National Science Foundation announced the discovery of a single boulder in the Trans-Antarctic Mountains, which are exactly what they sound like. It's a mountain range that runs under the glaciers in Antarctica, but runs basically across most of the continent. Which they say may prove that Antarctica and North America were at one point in history connected. The team reached their conclusion through analysis of the boulder's composition and grain. That's literally all it says. And I have so many questions because so let's break it down. So North America and Antarctica are about as far apart as you can be,
just about
continent-wise, because even so we think of the last supercontinent, which was Pangaea. North America was connected to Europe and Asia in these supercontinent, but like smaller supercontinent, a less supercontinent called
Right.
Laurasia, whereas the continents that are currently in the southern hemisphere, South America, Africa, Antarctica, and Australia, along with a couple others like India before it crashed into Asia, was in the southern supercontinent Gondwana. And to my knowledge, all of them in Gondwana in the south stayed together since like almost a billion years ago, maybe like 800 million years ago. And they stayed together basically until they split apart when Pangaea started to rift apart. So at no point in that was there space for North America and Antarctica to really be connected. So I'm very confused.
And it doesn't
I'll have to
seem
look
like,
into this on my own, just for my own purposes, because I'm
yeah,
so
because
confused.
it doesn't really seem like it was answered that well in the actual in the thing itself. So
Right. And it's like all it says is based on the boulder's composition and grain, where it's like, okay, granite in North America and granite in Europe, they might be slightly chemically different, but almost exactly the same. That's why it's granite,
mm-hmm.
you know? And I'm
Right.
sure if any igneous metamorphic petrologists are listening to this, they just got highly offended. But I don't understand igneous rocks at all. And that's what this would be. There's no way this would be a sedimentary rock that lasted from this long, you know? Or at least the chances are very, very small. So
Let's move on from this one. You said there was another
yeah,
one from over the weekend.
sure is. This one is less focused
Bad.
on our podcast.
Okay.
But so this is from July 18th, 2018. Therapy dogs help mitigate ADHD.
All right.
Sure.
I have no further questions because I have seen this happen.
Right. And it's like, yeah, I believe it.
Yup.
Researchers from the University of California, Irvine, announced the results of their study that the potential of therapy dogs in treating ADHD symptoms. The study, which surveyed children ages 7 to 9, found that the company of a therapy dog improved social behaviors of children with ADHD in 8 weeks. And that's what we got. So I guess 8 weeks and a dog, that's...
It is always fun the once or twice a year when therapy dogs come into school.
Mm-hmm.
And they, like every kid at some point, by midday has a story. They went up there and the dogs were so cute and blah blah. And it's like, yeah, absolutely.
Yeah,
Whatever ails you, like a puppy golden retriever will probably solve it.
Mm-hmm. So with that, I think we can move on to the main topic for today's episode.
Yeah.
And if all goes according to plan, there will actually be a blog post up, at least at some point. If you're listening to this the day it comes out, by the end of the day today, there'll hopefully be a blog post up about this topic.
So let's just say, to be safe, on the 22nd, on July 22nd,
hopefully,
on the Thursday, you can check and, with your
hopefully
morning
it
coffee.
is up right now, but...
Yeah, well. Whenever you're listening to this, just give a check, because we'll have a link to Gavin's blog also in the description. That'll be a fun thing to read. I'm looking at Pliocene-Eocene thermal maximum is
Close.
the topic.
There is another...
Paleocene.
Yes, there is another time period called the Pliocene that does exist. Yes. But
there was lots of words there that I've only been exposed to, like, verbally and not actually read them. So
yes. So today we're talking about an event in Earth history, not a group of animals or something like that, but an event in Earth history called the Paleocene-Eocene thermal maximum, much more commonly referred to as the PETM for short. And
way more commonly.
This is, after doing quite a lot of retrospection, this is probably as close as we're going to get to a dedicated climate change episode, for reasons that will become obvious.
Okay.
So this was going to be like the final prequel to a climate change episode. And I'm like, most of the things I'm going to talk about, I will talk about throughout this anyway. So it would just be reiterating a lot of things. And this event is actually incredibly well studied, probably in the last 25, almost 30 years, because of how similar it is to what we're doing to the planet today.
Well, I guess I'm a little bit sad that we're not gonna have a climate change episode. However, that's sort of our brand is, doing the slightly less covered things that
Right.
are, that form the backbones of stuff. So this is kind of on brand for us. So I'm looking forward to learning about this because even though what was it, the PETM
Yep.
is what you called it.
Mm-hmm.
I've never heard of that before, even though apparently it's more commonly used. But
Mostly just
uh,
because scientists love acronyms,
oh,
like
so do teachers. So do teachers. Don't you
and
worry.
and Paleocene-Eocene thermal maximum is just a mouthful, so we just say PETM.
All right, so let's get into it. So what do I need to know?
So this is an event, as you might have guessed, that takes place at the boundary between the Paleocene and Eocene epochs. If you remember back to our episode about the geologic timescale, once we get after the time of the non-bird dinosaurs, we start talking about smaller range, smaller slices of time. So these
Right.
are not periods; these are epochs. The next step down.
Right. So these are still, if correct me if I'm wrong, pretty big chunks of time, but slightly smaller than periods.
Um, the Eocene is relatively long. The Paleocene is only about 10 million years.
Okay. But this is like the next chunk of next step down from a period is an epoch.
Yes.
Okay.
Yeah. So this is an event at the boundary between the Paleocene and Eocene epochs. And so the Paleocene is the epoch right after the non-bird dinosaurs go extinct, which will obviously affect a lot of things going on in the world. But this event
Hmm.
in particular happens at around 55 and a half, 56 million years ago or so, just
So
for a
we
sort
are
of time reference.
strongly post-dinosaur at this point. Like
Yes,
dinosaurs are really not going to feature into today's discussion.
absolutely.
Okay.
And so scientists had kind of known that something happened at this time, but they weren't sure what, because they showed, or we've been seeing evidence of a massive die off of what are called benthic foraminifera and a large boom in a group of organisms called dinoflagellates. I do not blame you if you've never heard of either of these groups.
I was just going to be quiet until you said other things I could, say words on.
So, we've seen the evidence for this, but we didn't know what caused this, because usually when a group does super well or a group does super bad, there is a reason for it. Something changes that causes them to do less well. So, foraminifera are mostly, with an asterisk, single-celled organisms that live in the oceans. I think there are some freshwater ones, but they mostly live in the oceans. And they make sort of shells around themselves out of mostly calcium carbonate, the same
Mm-hmm.
material that clams make their shells out of.
Okay.
And so they basically mostly float in the water column. And I don't believe they're photosynthetic. They are sort of like carnivorous. They'll eat other microscopic things, essentially. However, the benthic ones, so benthic means on the seafloor. So these are ones that would live basically on the very bottom of the ocean. They experience a very, very large die off at this time. And then dinoflagellates are a group of what used to be called protists, even though protist isn't really a term that's used all that much anymore. Basically, another group of single-celled organisms. These some of them do photosynthesis, some of them don't. If you ever heard of a red tide, that is dinoflagellates that do that.
And what's a red tide?
Basically, when too much nutrients get pumped into the water, basically, mostly these days from human activity, from like fertilizer being like washed down a river and entering the ocean, it causes these things to really just explode in population. And when they do that, they suck all the oxygen out of the water and kill basically everything that's there. and they have this reddish color that basically turns the water red. It looks like it's full of blood, but it's not blood. It's these things.
Okay. And are they like these are alive, correct?
Yes. Yep. They
Okay,
are
I assume they're
single-celled.
anaerobic organisms.
So dinoflagellates, some of them are photosynthetic, so they
Okay.
produce oxygen. However, some of them, when there's too much nutrients, can suck up too much oxygen and take oxygen away from like fish and things, and just you'll see beaches just loaded and loaded with dead fish during a red tide. Um, Dinoflagellates themselves are also an extremely diverse group, because a subgroup of dinoflagellates are actually what make coral photosynthetic.
Hmm.
So they actually live inside the tissue of like the little tiny coral animal, which is basically an upside down jellyfish.
I'm not entirely sure I knew that coral was photosynthetic.
Yep, that's why they're so colorful, is from these dinoflagellates.
Okay.
The coral animal themselves is pretty much clear, like a jellyfish sort of is, but
Right.
these dinoflagellates live in their tissues and do photosynthesis and supply the coral with food.
Okay.
And so that's both of these groups. So the benthic foraminifera, the ones that live on the seafloor, we see a large die-off in them, whereas the dinoflagellates that live up in the water column, not on the seafloor, they explode in population all over the world. And so we'd seen this evidence, but we didn't really know why this happened until sort of the early to mid 90s, when our sort of isotope chemistry, our ways of analyzing different isotopes got much better. And so we've talked about isotopes a little bit on the channel, but do you remember what isotopes are, Mike?
If I remember correctly, it was when a particular atom had more or less electrons than you would regularly guess based on its number of protons and neutrons.
Close.
Okay.
It's when it has a different number of neutrons.
Oh, it's the neutrons that would change.
Yes.
Okay.
Yep. And so
I
when it
had a
has
one
a
in three
different,
shot.
yeah. So when it has a different number of neutrons, that makes it a different weight. Whereas electrons do have weight, but for most like non-atomic processes, the weight of electrons doesn't really matter.
Because it's so incredibly small, correct?
Exactly.
An electron versus a proton and a neutron.
Exactly. But when there are different numbers of neutrons, because if you have different numbers of protons, that's different elements. Carbon has 6 protons, oxygen has 8. That's what make them them.
Right. You cannot change the number of protons in an element and keep the same element.
Right.
You are right. Versus neutrons, you can monkey around with that a little bit.
A little bit. And so different climatic conditions will produce different ratios of the different isotopes. So the main isotopes in carbon are carbon 12, the normal one, or most common one, and then carbon 13 and carbon 14. Carbon 14 is radioactive. That's how you do radiocarbon dating.
Okay.
But carbon 13 is stable, not radioactive, and will preserve in fossils for us to test. And then
I
similar
think I
thing
can see where
with,
this is going.
right. And fortunately, those foraminifera and dinoflagellates are very, very good at sucking in and preserving those isotope ratios for us to look at.
Is this so? Let me, if I can guess and see where this is going. This is going to be part of how we know what what the earth, what the carbon in the air looked like across Earth. Going back hundreds of millions of years.
Absolutely.
Is being able to look at these, what you said, dinoflagellates is the correct term?
It depends. You can get these isotope ratios from quite a lot of different groups. Like you can even get them from like clams if you wanted, or even some like mammal teeth. I know quite a few people working on isotope stuff from like horse teeth.
Gotcha. Okay. So I so we are basically learning about how we know that the carbon problem today is a problem because of what we know about Earth's history and the carbon that used to exist.
More or less, yes.
All right.
Oxygen also is a very important isotope. Functions very similarly, but for a different use. So oxygen isotopes are representative of temperature. whereas carbon isotopes are representative indirectly of temperature because it's sort of how much carbon is in the atmosphere, which obviously affects temperature.
All right.
So, before we talk about the event itself, we need to talk about, as always, what the world was like before the event to understand what changed from beginning to end.
Okay.
So, as I mentioned, the Paleocene epoch is right after the extinction of the non-bird dinosaurs. And if you think of the time of the dinosaurs, you think of generally a very lush, very green, forested world.
Is that accurate? Because I do think of that. Is that
Toward
correct?
the end, yes. During the Triassic at the beginning, when dinosaurs first show up, it was pretty dry. There were still forests and things, but it was much drier than you think of typically with dinosaurs. But at the end of the Cretaceous, I mean, obviously there were some places where it was much drier, but
Right.
compared to today, it was much warmer, much more humid, generally, just globally, and much more forested. Partially because grass did not exist yet at that point.
That's still, we've talked about that before, but that's still
Yeah.
wild to me. Like grass
Mhm.
not existing just is
Right.
a real mind blow for me.
So this was a world that had no permanent ice. So even at the North and South Pole, there was probably still like seasonal ice because just like today, there was a certain time of the year where the North Pole gets literally no sunlight.
Mm-hmm.
And that was the case back then as well. So during those times, there probably was some like ice and snow buildup, but it was not in the form of these large glaciers like we think of with Antarctica today. There was no permanent ice on the planet, and it was still very much recovering from the events of the end Cretaceous mass extinction. But a really important thing that happens during the Paleocene is that we get, not at first, which we'll talk about, but most of the modern groups of mammals that we have today show up in the Paleocene. Almost all of them.
All the modern groups of mammals that we would know today show up in
Yeah.
the Paleocene. Do I have that? Okay.
So it would be things like, as large of groups as like your rodents. The first true rodents show up sometime in the Paleocene.
Okay.
The first primates show up, or at least things that you would look at and be like, that's a strange looking monkey, but it looks monkey-ish, show up in the Paleocene. The first horse ancestors, as we've talked about, show up in the Paleocene. The first like elephant ancestors show up in the Paleocene. However, that is at the very end, basically during this event. At the very end of the Paleocene is when those groups become much more widespread for reasons that we'll talk about.
Okay.
But for most of the Paleocene, it is very strange looking mammals. This is the first time that we get really large mammals, because the biggest mammals got really during the Mesozoic, the time of the dinosaurs, was like maybe like a very large rat to like at like top maybe like a possum size.
Okay, and what we're getting now are mammals that are just way larger,
Yeah, things much closer to
like primate monkey sized or even larger.
even larger, potentially up to close to like cow size.
Ooh, okay.
Right. So we get a very large jump very quickly as soon as the dinosaurs are gone, mammals start to do quite well. And that's not to say other groups weren't doing pretty well at this time too. The largest snake that we're aware of ever lived during this time. It's called Titanoboa, which is an excellent name.
We've talked about Titanoboa before, but it's awesome.
A roughly probably at most 45, 47 feet long snake. Massive snake. But that lived during this time down in South America. And we also get most of the modern groups of birds kind of show up around this time as well. So things are strange, but much more recognizable than they would have been like 5-8 million years beforehand. But we get lots of really interesting groups that I would love to go into. I fully plan on eventually doing an episode about just like things living during the Paleocene, because they're just very strange. And many groups that went extinct at or very shortly after the PETM, just because they don't have any even close relatives, let alone descendants, alive today.
That was going to be one of my questions. Was you said that there was, lots of mammals that we know today, like and you just answered. Are there mammals that we wouldn't recognize today that
Absolutely.
show up during this time? And it sounds like the answer is yes.
Absolutely.
So I'm looking forward to that episode eventually. But that is not the subject of today's episode. Is
Exactly.
all the things that were alive during this time.
So that's sort of just setting the scene. And then things get really, really hot. This event is called a thermal maximum for a reason. So this is not the hottest Earth has ever been. That is likely sometime way back, when Earth was forming, when everything was lava.
Or like 2032.
Well, we're not there yet, so we'll see. But it is one of the hottest time periods or events of the Phanerozoic. So basically when we had complex life. The Cambrian period was probably the only period. So this is the very first period when we start to see complex life, around 540-ish million years ago. Is the only time period that's like consistently as hot as this was. But just sort of for reference, the average global temperature in the period of 1950 to 1980, so before our impacts really started to affect the climate, the average global temperature was around 14 degrees Celsius, or around 57 if you use freedom units, like my God do. So for reference,
can I pause you real quick on that?
Absolutely.
So I've been thinking on the whole Celsius versus Fahrenheit debate, and you tell me how crazy I am if I'm just a stupid American. But for like regular daily temperatures, like when I'm like going on weather.com to figure things out, Fahrenheit seems useful because it's basically a 0 to 100 scale, and anything less than 0 like is dangerously cold, and anything over 100 is dangerously hot. That, to me, that seems useful for like the average human's daily life. Am I wildly off?
Sort of.
Okay.
It has its uses for sure.
I get it'd be easier if we had to pick one or the other. I understand all the reasons why Celsius is better, but
Celsius makes much more sense from like a nature perspective, because 0 is when water freezes and 100 is when water boils.
Right, that's why I see like for scientists, like it makes way too much sense for scientists to go ahead and use Celsius.
Right.
But to me, it just seems like for like
mm-hmm.
we can. It seems like it's one of the things like Fahrenheit has a limited purpose.
Personally, for myself, I would prefer if everyone switched to Kelvin, because that is a linear unit that has like a ground in 0. Whereas I think we've talked about this before, where it's like the difference between 10 and 20 Fahrenheit is not the same amount of like kinetic energy, because that's actually what temperature is measuring, is kinetic energy of whatever you are measuring.
Right.
So the difference between 10 and 20 Fahrenheit is not the same as between 100 and 110.
But for Kelvin, it is.
For Kelvin, it is. And so that's why I like Kelvin. I understand that nobody will ever use Kelvin in their real life.
I mean, I think we should just start. Maybe that can be our new bit to start the podcast. Is we'll just say what the temperature is in Kelvin where we are.
Maybe we'll talk about it. Anywho,
we'll talk about it where you can say no. Anyway, sorry to derail the podcast, but I had seen this recently, and it was something that I wanted to bring up with a smart person.
That was a good digression. I like it. But yeah, so average temperature between 1950 and 1980, in real human terms, 57 degrees Fahrenheit on average. The Paleocene, on average, not including the PETM, the average was around 24 degrees Celsius, or around 77 degrees Fahrenheit.
That's massive.
It was very warm. And so, that's sort of...
And that's the average. That
was the average.
Wow.
Again, that is excluding this big warming event.
Okay.
So it's just in general very hot. However, during the PETM, the temperature increased by, and isotope analyses are imperfect. They don't give an exact, they give a sort of a range. But from what we can tell, the temperature increased by between 5 and 8 degrees Celsius, or in, I guess, real person terms, 7 to 12 degrees Fahrenheit.
I mean,
Which might not seem like a lot.
until you remember where you're starting from.
Yesterday might have been 12 degrees cooler than today. And it's like, you notice it, but it's like, you can still go outside. You can still go do stuff. You know, it's not oppressively hot, you know. However, to have that much of a global change in average, and keep in mind, that's an average temperature. There are some areas around the equator where we have evidence from where the surface seawater temperature, and this is not a number that I actually have on our sheet. This is a number that I just sort of remember from doing the research. So the surface of the ocean was around 32 to 34 degrees Celsius. That is well over 100 degrees. So it got extremely hot.
It, like you said before, a 12-degree difference from one day to the next, you notice it, but it's not that big a deal. But when things used to be one way, and then the average day is 12 degrees warmer, like that's gonna
exactly
like that's huge. And this is during the PETM event, you said, correct?
Yes.
Wow.
So
why? How did this happen?
And
Who
we
did this?
we will get into it, but something that I want to make very clear is, so scientists today are freaking out about a potential we've pretty much already warmed the climate 2 degrees, and we're seeing things happen like the big heat dome that happened in the Pacific Northwest. Climate scientists put out some research as quickly as they could while still being thorough, because they understand that these days people have very short attention spans. So within about a week to 10 days, they put out some climate modeling saying that, like, without the warming that we have caused, that event would not have happened. So really bad things are happening with just 2 degrees. Like 1.5 to 2 degrees Celsius is real bad, let alone 5 to 8. So
yeah,
and all of this happened. So
I have nothing to add.
Have you looked at the next part of our sheet yet?
No, not yet. There's a lot of big words in this one, so I'm trying to go one at a time.
So if you had to guess, this is a very short event in geologic history. How long do you think that this warming took?
You said it was a long or short event?
Short event. Very short.
In geologic history? I'll 10,000 years.
Very close. That is sort of the lower end of the range of what scientists think, is that this warming took between 10 and 20,000 years. So let's do some quick math here. So that works out to somewhere between, if we take, the high and low of both the temperature and the time, somewhere between 0.00025 degrees per year and 0.0004 degrees per year. Relatively small.
You wouldn't even notice it.
No. However, the reason that this is so highly studied is because this is the closest case study in Earth history that we could find to what we're doing today.
Is it really? These numbers are the closest we have to what's going on now?
Yes. But just for comparison, how much we're warming the climate today.
Oh, no.
So we've been warming the climate roughly at a rate of about 0.0075 to 0.013 degrees per year. And based on my math,
that's bigger.
Much larger. Around 30 times as fast as this event. So again, what we are doing is absolutely unprecedented, but this is the closest thing.
I talked to my first climate change denier for the first time in a while this past week.
Mm-hmm.
And he is not a listener to this podcast. He doesn't know what a podcast is. But just, I just don't know what to say. And not even, but like, even people that are fully on board, with like climate change, that like understanding that number, like this is the first time I've ever seen these numbers, but just understanding the scale of what we are doing is really hard for at least me to wrap my mind around. And I imagine other people are the same.
Yeah. It's looking at it from a geological perspective, it is absolutely horrifying. But we're going to move past that slightly. So, what actually happened? Exactly. So, what actually happened to cause this? So, like pretty much every large event in Earth history, is a pretty complex combination of things. There is no single cause. People actually looked once we discovered, okay, this happened. As we talk about with mass extinctions, pretty much everyone immediately was like, okay, my thing is my hypothesis is the one thing that did in all of these animals. But in reality, it is a much more complex mixture of things.
Right.
So the thing that most likely kicked it off is a large amount of volcanism, which will not surprise you if you've listened to any of our things where we've talked about mass extinctions.
Right.
And so this was not a particularly large one. It was still quite large. So this one is called the North Atlantic Igneous Province, and it had around 500,000 square miles of total area, centered on what is today Iceland. And that's roughly twice the area of Texas. So not huge compared to some of the other ones in Earth history, but still quite large.
Right.
And this province, this North Atlantic Igneous Province, lasted around 6 million years total, but a significant pulse of activity happened around this time. So that is sort of the main kickoff event that most scientists sort of suspect. However,
do we think it was, I'm assuming it wasn't like one volcano, but a series of volcanoes located in roughly the same area?
Right. And so this was mostly caused by, like it's called the North Atlantic Igneous Province. Around this time, North America was still splitting from Europe and creating the Atlantic Ocean. During, when Pangea was around, the Atlantic Ocean didn't exist because all the continents were smashed together.
Right. It was all just ocean.
Right. So the Pacific Ocean technically sort of existed because the west coast of the Americas was exposed to the ocean, but the east coast, what is today the east coast, was connected to other continents. So when Pangea broke apart, that formed the Atlantic Ocean. And so this was still happening. The continents were still moving apart at a pretty significant rate, which can sometimes cause lots of magma to come up as the continents are pulled apart. So that's what was sort of causing this.
Right.
And there are other things that people sort of propose around this time that either aren't as likely or we don't just have great evidence for, but they're worth talking about because it's like, I mean, yeah, technically, I guess that could have happened, but we don't see it.
Mm-hmm.
So one, as always, with weird climatic events, some people have suggested a large asteroid hit Earth. Which, sure.
How often does that happen?
Not often.
Yeah.
Like more often than you think, but not often.
Okay.
So, obviously there's the big one that hit Earth 66 million years ago. It's not like it happens every 66 million years on the dot. There were other large ones that happened in the Cretaceous, other than that one, that weren't as big of a deal. But if even like a moderate sized one that wouldn't, obliterate life on the planet, if it happened to hit rocks that have a lot of carbon in them, like a limestone, it would basically vaporize all of that rock and pump that carbon into the atmosphere.
I assume that would be a pretty quick process.
Yes. So that's it sort of fits the symptoms, but we don't find a crater. We don't. There's some other evidence, but it's like from what I could find, it's not that well supported of a hypothesis. So we're just gonna move on.
Mm-hmm.
Another one, which again is very hard to find evidence for because this is not evidence that you would ever find in rocks, but with some funky things going on with Earth's orbit around the sun.
Oh,
With some weird cycles that I guess
Hmm.
work out with physics. Where just so happens that we get relatively close to the sun compared to other times.
Do you remember what those are called? Because I at one point
I
knew the
don't.
name. Yeah,
Um,
I will look it
there
up.
there are other cycles. Like Earth has many natural cycles. One that you might
Yes,
have heard about are called Milenkovic cycles.
that was what I was thinking of. Is that not what
That's
I'm?
not this.
Okay.
Milenkovic cycles are relatively recent, like glacial cycles. So that's not this.
Okay.
So again, apparently the physics for it works out with okay, Earth might have been closer to the sun at this point, which if there's extra greenhouse gases in the atmosphere anyway, being closer to the sun would just increase the warming. It obviously wouldn't put more carbon in the atmosphere, but it would make the carbon more effective at trapping heat.
Yes.
So, again, not something you would find in the rocks, but worth mentioning because it's like, I guess, sure, that might have
Yeah.
happened. Who knows?
Throw it all at the wall.
Right. One that's been talked about much more credibly because there is some rock evidence for this is this volcanism burning up a bunch of peat. If you remember to our fossil fuels episode, peat is sort of the precursor to coal. And so it is essentially just like non-lithified, non-hardened coal. So if some of this volcanism was able to set that on fire, that would burn up a bunch of carbon and put it into the atmosphere. So there's some evidence for it, but all that peat would have to be relatively close to the volcano to begin with. So it doesn't seem like that would be that large of a player. Like it probably didn't help, but
Yeah,
it
it
wasn't
could have affected it, but may not have been the starring role.
exactly. The big thing that most people sort of agree on these days is that the volcanism triggered methane to be released from deep down in the ocean. So, a little bit of weird chemistry here. So, methane, which as we talked about in I think yeah, also the fossil fuels episode, is typically a gas. However, pretty much any gas can be turned into a solid if you put it under enough pressure and keep it there.
Mm-hmm.
It also helps when it's cold. So even back during this time, the bottom of the ocean was still cold. It was warmer than it is today, but it was still cold, much colder than the surface. And it was cold enough and had high enough pressure to keep this methane in sort of a crystal-y sort of form when bonded with water, like chemically bonded with water. And so these are commonly called methane hydrates, or sometimes you might see them called methane clathrates. Basically, when things fall to the bottom of the ocean, they can be turned into methane as they're being sort of decomposed. And sometimes if sediment gets put on top of them, they will get turned into oil like that. But if they're not, sometimes they can just stay on the surface of like the bottom of the ocean instead of being buried and turn into these methane hydrates. But they need to be cold to stay solid. And so sort of the hypothesis is that warming the planet just a little bit, and the planet was already relatively warm, right?
Mm-hmm.
So warming the planet just a little bit from that volcanism might have sort of freed some, not all, but just a little bit of that methane, which then goes into the atmosphere.
And then we'll trap more heat.
Exactly.
And it becomes a cycle.
Exactly. That is what we call a positive feedback loop. Which
I was
many
going to say
scientists,
awesome, but not awesome.
right, which many scientists are very concerned about today because there are very many frightening potential positive feedback loops proposed with our current climate change.
I've been a downer like this episode because I'm thinking about the relation to how all this fits in, like today's world. But
Mm-hmm.
like thinking about it just in isolation, like we're trying to talk about the history of, history of Earth in this particular time. Like in isolation, this is fascinating stuff. So I shouldn't be
Oh,
such a
absolutely.
downer because this is just about something cool that happened, millions of years ago. And the fact that it's also relevant today is not the main thing I should be focusing on.
Well, I mean, that is why we're talking about it, because like I said, it is an interesting event that is relevant to today. So
And
that
is
is,
also interesting on its own merits.
yes. And so that is sort of how all the carbon got into the atmosphere. So what did it do then? So obviously, it warmed the climate. That's why we're talking about this. But
Hmm.
something else that we're seeing also today is that it acidified the ocean. Carbon dioxide dissolved into the water will create what's called carbonic acid, which makes it real tough for things that make shells out of dissolvable things to live. Everything from clams to, very importantly, those benthic foraminifera. That is probably why they had such a die-off when they did.
Can you explain that one more time? I think I got it, but
So carbon dioxide, and if you maybe you remember in like high school chemistry, you put sort of an indicator solution into a cup of water and you breathed through a straw into the water and made it change color.
This sounds familiar. Yeah.
That is because the carbon dioxide that you breathe out and that is in the atmosphere, when it is dissolved in the water, creates an acid called carbonic acid. We don't have time to go into chemistry, but trust me, it does. Um, so that acid sort of interrupts. It doesn't just like literally dissolve the shells of things that make their shells out of calcium carbonate, but it interrupts the process of them forming their shell to begin with. So it just makes their shell sort of flimsier and less sturdy.
Right. Okay.
And so those benthic foraminifera that we talked about at the beginning, which is how scientists first noticed this event to begin with, this is probably a large reason why they died off in as significant numbers as they did. And also,
Yeah.
it probably won't surprise you to learn that coral reefs also didn't do so great at this time, like they are today.
Is it? How hard is it to have coral reefs kind of come back or to start new ones? Like I imagine that's a process that
Corals
takes.
do actually spread relatively quickly if
Oh,
the
really?
conditions are right. And most people would kind of think, okay, it's real warm. Corals only live in tropical areas. That just means they could live in more places, right? And it's like, well, yeah, sort of. But they also have very narrow pH ranges, acidity ranges that they can tolerate. Otherwise, the dinoflagellates that live in their tissues that allow the photosynthesis to happen, once the pH range or even like the salt concentration range gets out of what they like, the dinoflagellates will leave their tissues, and that's when coral bleaching happens because all the color is gone and the coral animal itself is clear. So you just see the calcium carbonate that the corals make the actual reef out of.
Okay. Like that. So the current is it a crisis right now? Coral reefs.
Oh yeah, big time.
So, but it is one that is theoretically solvable or at least fixable because coral reefs can spread somewhat quickly.
Right.
Okay.
Not coral reefs are capable of doing it. The ocean takes a while to regulate itself.
Right. Which
So
is a longer process.
right. Well, some other things that happen around this time is when oceans tend to get more acidic and also just warmer, they are able to hold less oxygen. So there was just generally less oxygen in the water, which, especially
Not
for things
great for
that can't
things.
exactly, just generally not great. On land, however, uh, in some areas we see much more rain. More heat means more evaporation, which
Mm-hmm.
means more rain, which means flooding, typhoons, things like that. Whereas in other areas, there was evidence of some pretty severe droughts. You know, like you would also expect if the winds aren't happening to blow over a body of water to pick up that evaporation. You know, if you're not getting rain and it gets hotter, you're just going to get, you know, if you don't get rain to begin with, you're just going to get less rain. Like we're seeing in like the southwest of the United States today.
Right. This is all post-Pangea, correct?
Yes, this is well post-Pangea.
Okay, I wanted to, because I remember before you said that, you know, like the middle of Pangea, there, you know, wasn't a whole lot of waters because there was no water around. But this is after that time.
Right. So, yeah, some areas get much less rain, other areas get much more. Which is fine if it happens gradually, but it didn't and isn't today. And then lastly, just sort of an asterisk for some things that we know happened, but don't really know how much they happen, where when ocean temperatures change, the currents change. So it's like it's really hard to understand the currents at all this long ago. Ocean current modeling is very, very difficult because there are so many variables that we don't understand.
Right. I mean, there's so many butterfly effects here. Like
Exactly. And so we don't know what they were in the Paleocene, but it's like you kind of have to assume that they changed significantly because of this. Just because ocean currents are mostly driven by density differences. And if everything is just getting hotter, you know, the density gradient is going to decrease. So some funky ocean current things probably happened, but it's hard to tell that for sure. So, these are some of the climatic things that happened. And obviously, in response to that, animals had to do something. You know, animals and plants as well. You know, life had to respond somehow. So, what did life do? Well, a really odd thing that happened is that animals got much smaller. Mammals especially. What was that?
I was gonna say to use less energy, but I'm not entirely sure if that fits with what was going on the way you're describing it.
No, it is actually a heat loss thing. Where, as I think I talked about in the elephants episode, it is easier, or probably the sauropods episode actually, it is easier for bigger bodies to retain more heat. That is sort of a surface area to volume ratio thing. Where it's like
these guys wanted to get rid of as much heat as possible.
Right, so they wanted to maximize their surface area while decreasing their volume. Because surface area is how you radiate out your heat. Because mammals, you know, warm-blooded, they create their own heat. But if the heat around you is, you know, the air around you is warmer than you are, it's very hard to decrease your own heat. So you get small to not get heat stroke all the time.
And that makes smaller animals. Okay.
Yeah. Basically the opposite effect of why most mammals that live in like during cold times, why there were so many large things around during the Pleistocene, the Ice Age. There were just lots of large mammals around because they wanted to keep in heat. It's the exact same phenomenon, just happening in reverse. So, mammals got smaller, and there was definitely a turnover. Not quite an extinction event, but a turnover from the old weird mammals that we talked about earlier to the modern ones that I was talking about. You know, the first horse relatives show up here, the first elephant relatives show up here, stuff like that. Like I said, corals do pretty bad. Overall, globally, a dip in diversity, but not a mass extinction level 1, which kind of sounds hopeful for us, but for reasons that I'll kind of break down later, maybe not.
I was going to ask, but I'll let you get there.
So we'll move on to plants here, but just really quickly, because plants, I barely understand anything about modern plants, realistically. So, but from everything I could find, plants, there are definitely some extinctions, but they mostly just move to weird spots. Like we saw rainforests very far north.
Oh, I was gonna ask what counts as a weird spot for a plant, but yeah, like a rainforest far
Right.
north is not something I would expect.
And we see pine trees or conifer trees also having to retreat much more north. A lot of the good plant material from around this time is actually from Wyoming. Um, and you can see beautifully the transition in plants from before, during, and after, where it's like before, this was an area that was able to support conifers, things like your pine trees. Um, During the event, it goes basically to tropical rainforest, and then dips right back to pine trees afterward.
Hmm. I mean, that's all I really got is a that seems interesting, but
Right. But obviously, animals need specific plants. Herbivores eat specific plants. So it's like they
right.
needed to move and shift around, and sometimes they just kind of couldn't, which is why we have the turnover. But very broadly, no major extinctions. So how does this whole
Huh.
thing end?
That took one of the questions out of my mouth here.
Mm-hmm. So this whole event, so the warming itself only took 10 to 20 million or 10 to 20,000 years. But while it was warm, was around 150,000 to 200,000 years. Still geologically very short.
I was gonna say that is the timescales we've been talking about in this podcast. That is incredibly short.
Yes. So from start to end, maximum around 200,000 years. So after the initial warming, then there was some interesting things happened that make some sense if you understand the way Earth works. So a lot of those things that were really thriving, some of those dinoflagellates that were doing photosynthesis, they take in carbon when doing photosynthesis, just like plants do. All those things living it up in the top of the water column die, right? Then
Mm-hmm.
they sink down to the bottom of the ocean, and that carbon gets stored there as, rock or potentially more methane. So that's one way to remove carbon from the atmosphere. Another way,
That doesn't seem like particularly efficient, but
no. But, well, like I said, they were thriving with a capital T all over the planet.
okay.
So they were doing a real good job. And even today, trees get all the credit for doing photosynthesis and producing oxygen. Like oceanic, marine, photosynthetic, like single-celled organisms are an extremely important part of the carbon cycle. Like take in as much, if not more, carbon than trees. So
Wow.
throwing that out there.
Wow.
Granted, the entire planet was covered in trees at this point in time, where it's not today. So who knows? But the most often major carbon sink that was sort of talked about this, removing all the carbon from this event, ending this event, comes from actually weathering. We've talked about before, and I don't remember which episode, but increased weathering of many different kinds of rocks can, just like the chemistry of how certain minerals are weathered, removes carbon dioxide from the atmosphere and turns it into clay minerals. Again, weird
Okay.
chemistry that we don't have time for.
right.
So all that higher rainfall
Right.
meant that more weathering and erosion was happening in general in the areas with more rain.
I'm following you so far.
More heat also generally makes chemical reactions happen faster.
Okay.
So that helped. And then all of that new volcanic rock from the North Atlantic Igneous province, all of that was being weathered and eroded. So that helped reduce the carbon that it put into the atmosphere. And then also around this time was when the Rocky Mountains were starting to build. So just as sort of the Himalayas are a big carbon sink today with their weathering, when the Rocky Mountains were being built, that just gave much, much more rock surface area to erode to begin with.
Can you just one more time go over how weathering and erosion are a carbon sink? Because I'm not sure
Yeah.
I followed that.
So when minerals sort of like weather chemically. So there's one way to do it where it's like, you have water flowing over them that just moves sediment from one place to another. That
Right.
is erosion. Whereas weathering is a chemical process. So certain minerals, just in the process of, think of it sort of like atomic decay, where it's like you have uranium that, when it is radioactive and decays, turns into lead by throwing off certain parts of itself, protons.
Okay.
So certain minerals, usually for radioactive things, they need to be sort of like interacted with in some way. Some of them will just do it spontaneously, but some of them also need a little bit of stimulation to do it. So these minerals are interacted with the carbon in the atmosphere that then break down into clay minerals. That's just a broad group of minerals. And clay minerals often have a lot of carbon in their like atomic formula
Uh-huh.
taken from the atmosphere, and the rest of their chemical formula is based on whatever the mineral that it weathered from was.
Okay. Let me make sure I understand this, because I
Yes.
think I have a better idea now. So with more weathering and erosion, there's, more surface area, and it's easier for the rocks and other things on Earth to absorb this carbon from the atmosphere, turning it into clay.
Yes.
Is that about right?
Yeah.
That makes so much more sense. And that makes sense as to why, like, mountains being formed, like the Rockies or the Himalayas, like you said, would be a pretty significant source of, of carbon sink to get,
Mm-hmm.
get that out of the atmosphere.
Yeah.
Wow. I never would have considered that.
That is something that I didn't learn that in undergrad. I learned that in my graduate school.
So, how much money in the U.S. federal budget do we need to build more mountains?
That's
Because I think that
probably
solves several problems at once.
that's probably not a sustainable option, because we'd probably be using fossil fuels to build those mountains. So that
Musk and Bezos and whoever, get on that.
no, they're just gonna go to space instead. But so
I hope
now
they have a great time when they're up there.
So that pretty much ends the PETM. Afterward, things go more or less back to what they were beforehand. And then in the Eocene, things gradually get much warmer. Like the peak temperatures in the Eocene, like sustained, are about maybe slightly less than like the temperatures we see during the PETM, but it got there much more gradually. And things we didn't see the big turnovers. We didn't see lots of different, weird random groups dying off, because it happened gradually. So now I'm going to circle back just briefly to how this is different than today. Because like I said, this is the closest thing to today, but it's not the same.
It's not the same thing. And when we're talking about the closest thing to today, and you say there wasn't a big mass extinction event, you would, at least I think, you'd be forgiven for having a question pop up like, well, climate change might be bad for lots of reasons, but should we not be worried about mass extinction events today?
Right.
So tell me why that is not the case.
Number one is that we're starting at a much lower temperature, because we still have ice on the planet. And
so far.
Right. And so ice does something that you probably don't think of it doing. You probably notice this if you live in a place where it gets snow in the winter. But when you're driving, it is very bright out.
Yes.
Because snow and ice reflect sunlight.
Mm-hmm.
They do a really good job of reflecting sunlight back out into space. If you have a lot of ice that the sun hits, it's called the albedo effect. It is basically a reverse greenhouse. So if we melt all the ice, that creates another positive feedback loop.
And that's one of those problems that it seems like would become next to impossible to fix on any kind of a normal human timescale.
Right. And not only that, but having lots more ice covers seawater, which is quite dark. And obviously dark things absorb much more light than they reflect. So that just increases the overall light and therefore heat absorption of Earth. So that's big difference number one. Big difference number two is that because there was no ice at the time, sea levels were pretty high because all that water was not stored in glaciers. Whereas today, melting ice will raise sea levels.
Which presents a whole new kind of problem.
Exactly. Which, again, not a problem really for the environment, a massive, massive problem for humans, because we like to live near the water.
It's nice there.
Yeah, so again, and this kind of comes down to the whole thing where it's like, everyone's like, save, especially the marketing around climate change has changed significantly even since I was younger. It's like, save the planet, save the planet. It's like, no, save us. The planet's gonna be fine. Humans will not.
Planet's been here for long before us and will continue to be here for long after.
So that's another very key difference. A really, really big key difference that I think probably helped there not be too many extinctions at the time was that the plants were able to move as they did. Like I said, there were some plant extinctions, but like I said, with like the pine tree to rainforest back to pine tree thing, they just sort of shifted north and then shifted back south. So plants can't do that today because we have so badly fragmented nature.
Mm-hmm.
There's not a continuous, stretch of land where if pine trees in Wyoming needed to move north to like not go extinct, where they could do that. Because there's so much human occupied, human managed land between where they are to where they need to go. So they're not like birds. They can't just pick up and move there. They need a continuous swath of land for their seeds to fall on, that to grow into a tree, for that tree's seeds to land on. So how badly we fragmented the ecosystem will really impair how well animals and plants will be able to move to where they're adapted to living.
I know you said save the humans and all, but the animals and other species that are affected by that. That's what I think kills me the most.
Mm-hmm.
Is the habitats destroyed and the animals that are without homes. That's always what gets me.
Yeah. So those are some of the big differences between then and today. Also, that we're just doing it much faster.
That's what strikes me as like one of the biggest problems is just how fast this is happening.
Some estimates say that we will likely get to the total amount of carbon that the PETM likely produced in about 1,000 years, as opposed to 10 to 20. So
this is, the plan as of right now is that we are not going to have an official climate change episode.
Right.
But you can sort of use this as a sort of a primer on the kind of things this podcast would talk about, which is some historical context for what's currently happening and and what happened previously and why the current moment is different. For those of you that listened all the way through, there's, as Gavin said, there's lots of similarities, but there's lots of reasons to think that it's different now. It's different this time.
Right.
And would be significantly worse.
For us.
We weren't around back then, but yes.
Right. But it's like many animals will be fine. Many animals might be like those dinoflagellates where they're living it up with warmer temperatures. But we will not be one of those organisms. So, yeah, that's and we kind of have the PETM to thank for likely us existing at all, because like I said, primates really did very well afterward. They were kind of around, but they didn't really spread until during and after the PETM. So primates were a group that did quite well during the PETM. So thanks. But I'd really like to not do that again, if we could.
Preferably if possible. So this episode kind of ended on a downer, but for those of you that were able to make it all the way through, quick preview. I believe, correct me if I'm wrong, Gavin, but next week I believe we have a special episode that is coming up.
We sure do. We're gonna have a couple guests on talking about a very, it shouldn't be, but it is a rather controversial topic in paleontology. One that has been very important to me, and one that I think we even teased way back in like episode as early as like 5, maybe even the first episode.
I am very much looking forward to listening to a whole bunch of smart people talking, and I will just casually poke my head out to say, can you tell me how to pronounce that word whenever is appropriate? But this has been episode 32 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Mike, and that was Gavin. Gavin, save the planet, save the humans.
I'm doing my best.
Aren't we all? Take care, everybody.